Okay, the recording has started. Okay, so let's resolve this exercise. As I mentioned before, we are going to run a hierarchical clustering with CAM-RBAN and the k-means with CAM-RBAN. So in order to do that, we are going to need this G table from the exercise 12.1.4 that you get today. So let's start. So the first thing that we need to do is we are going to transform this G table that we have in a differential gene expression. So we are going to select only such genes that has a p-value below 0.05. So let me go to my R. In principle, we should have already, Melissa should have already these objects. So copy and paste. So if I run this, I get this table. So let's take a look of how the table looked like. Now DG table. Okay, so this is how it should look the table. Remember, this is a table that we add all this mean and standard deviation and everything, and then at the end we add also the differential expression analysis. Okay, so we have everything, and we are in this table we are selecting only the values where p-values below 0.05. Okay, if you still are curious, one thing that you can always do is, let's suppose that you want to see how different are they. So you always can check, no, is, for example, here, no, this is 17, 18, 18, that is a pure line compared with 15, 16, and 18, compared with, that is the hybrid 18, 19, 20, and the 16, 16, 18. So by average, looks like, yeah, it may be different, but you always can check this. As I said, that is with the real experiment. And with this experiment, you know that we have all these problems. Okay, so first step done. So let's go to the second one. We want to put as a row names the ID, okay? So we go here. So we run this. And now, if you see, we have changed the numbers. Now, instead of the numbers, we have the gene ID, okay? In this case, these are gene IDs that show that probably are genes that were generated with cufflinks. So it's why, well, STINTA is why you have this MSTRG instead of the regular 8 Arabidopsis thaliana genes. And then once we have that, the last thing is we want to select only the expression data. So we select, we're going to select only for the column 2 to the column 13. So we do this, and now we run ahead. You see that we just keep only the expression data, because expression data is the input that you need for any cluster analysis. So once we have done that, we are ready to run the exercise. So first, we are going to calculate the gene expression distance. It's with a very simple distance function. Let's separate this. Dimension, we are going to calculate the distance. By default, we are going to get the Euclidean distance. So you are curious how they looks like. So keep in mind that we are calculating the distance for the genes, okay, not for the samples, okay. So that is how we look the distance for the genes, I guess. Okay. So once we have done that, the next is performing the clustering. So the first is to perform the cluster. We are going to use this genetic distance, and we are going to use hclust as to perform the hierarchical clustering. So let's run the hierarchical clustering. Done. Okay. Then you have always, of course, you always can explore how this object looks like, because some of them are complex objects. So as you can see, the hierarchical clustering gives me several options here, Car, distant methods, labels, order, height, or merge. So for example, we want to go for the distant methods. It's telling us that it comes from the Euclidean distance. Then we want to do the plotting. So I add a line in H1000. So this is the plot. Okay, this is how looks the plot with the line. And then let's say that we want to say, okay, we want to have 1, 2, 3, 4, 5, 6 clusters. No, I don't know where we have 6 clusters. 1, 2, 3, 4, 5. Probably here. We have 1, 2, 3, 4, 5, 6. So around, yeah, I say 1,000, but yeah, 5,000, for example. So we go here. We say align 1,000. Well, let's try 1,000. So we plot this line. This time probably we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So probably that line does represent quite well 6 clusters. This one represents more clearly 6 clusters. Okay, so this, okay. So that line represents 6 clusters. So this is not, but this one. And then finally, we are going to cut the tree for 6. So we run this. Okay, so we have gene cluster for 6. I think that I repeat the command because in this case I did with 6, and then I plot the clustering, but I wanted to put K6. So let me go back and fix this problem. So this is K6. And once I run this, I want to check with the table how the number of this per cluster. Okay, so let's do this. Okay, so that is the number of genes per cluster. Someone of you asked me why you have different results, and the thing is because they are not very good cluster. They're not solid cluster. If I run this again, but in this case I get the same, I think. Yeah, for this hierarchical clustering I get the same. I think that with k-means it may not. So okay. So as I said, this is the number the cluster that we have. And the problem is that we have 5 and 6. The cluster number 5 and the cluster number 6 have only one representative. So I'm not sure how useful is this. We still can keep them and play with cluster 6, or we can change it, So potentially we can change that. So the proposition that I put here is to run this, but with 3 clusters only. So if I do this, and then I copy the table and paste the table, yeah, so we will do the same thing just with 3 clusters. So this is the solution for 3 clusters. Okay, so at the end we merge, I guess that's cluster 5 and 6 with cluster 4. So that is, I guess that this is the thing that we see here, no? We are merging probably some of these clusters, I would think. Okay, so that is in terms of having clusters. So then once we have the clusters, the next step, the next exercise will be to visualize this cluster. And to do that, we need to use tables that it can be more complicated to play with. But as I said, I put just the command here, so I hope that still should be easy. Now I already upload this library, so let me copy and paste this. So one, you see that now it's advancing this because it's telling me that I'm not finishing this sentence, so I can go here, copy this. Yeah. Okay, and then the last one. Okay, so if I do that now, if I run this, let's check what we have in gene cluster 3. Okay, this is how looks the gene cluster. It's already telling me that I have a table with gene and cluster, and then the number of cluster for 253 rows. So that is exercise 1.3. Okay, so that is the first part. Again, second part is trying to retrieve expression table and convert also in a threefold. And the reason is that when you are using ggplot doesn't accept table like normally. So you need to transform these tables in something that you will see. So let me go here step by step, and I will show you how. No. So first we select from the G table only the differential express genes. When we want to put the raw names, we want to select only the means. So it's why I'm selecting rows 14, 16, 18, and 20. And then we want to add this gene with the row names that we already put before to have this gene ID. Okay, so to this point, I have let me show you what we have first. Okay, so to this point, if we take a look of this table, we have a simple table with the expressions and then the gene ID at the end. But we want to transform this in something in a table in which we have the genes here in the first column, and then in the second column we want to tell if we have mean 724, mean call, mean 24 call, or mean call 24. Okay, and then we will have the expression value. In other words, each of the genes will have 4 rows. Okay, and each of the rows will represent one of these. So to do that, we are going to do the next operation, that is have this table with gather. So we'll do this, and now we take a look of this TT table. Sorry, TDE TT table. This is how it looks like. You know? So you see that we have genes and conditions and expression, but we want to sort everything by genes. So it's this last command that you can see here. So we run this, and now we run it again. You see we have for this, each of the genes, we have 4 rows, each of those with expression, because this is the format that we need to use ggplot in the way that we want to use now. Okay, so once we have that, we want to join the results tables with this one using an inner join. Let me fix this. So run this one. Okay. So now let's see. This is how it looks. GDE means cluster. Okay. So we have gene, condition, expression, and then we have the cluster. No, we have the extra one. And once we have that, is when we finally are going to use this ggplot. So we are going to feed ggplot with this tool, and then this is a ggplot command. So we have aesthetics, condition, and expression columns, and then we want to group by gene for the geometrical line, and then we want to have some summary stats, and then finally we want to also have different grids. So we want to have as many rows as cluster we have. So we do this. See. So let's run this. Okay. It gives me some message that say that summary function, no summary function supply, defaulting to min, but at the end is the thing that we wanted, to have a min. I didn't have much time to fix that part. So this is how it looks like. So we have the different gene clusters and then the tendency of the genes. As I said, not very useful for the data set that we have, but it may be useful for other data sets that you may have in the future. Okay, questions that you may have about the first exercise. I don't know you, but I'm starting to overheat. Question, what is exactly a T-block? A T-block is one of these objects that is associated to this specific program that is deeply, that it doesn't represent, well, it's a specific object that has some specific characteristic that I don't know which one are, but it's a specific object of this package of dtblir, or dplir, sorry. This package from here, from the tidyverse, and then this dplir. So I will imagine that it looks like it's a data frame and a special data frame associated with this package. But I don't know anything about any other things. Maybe it has some different slots to store other type of information. Other question? Okay.
Yes, one.
Yeah.
The ggplot function give me an error, but it plot correctly the cluster. I don't know why. I passed error on the chat.
Yeah, I mean, I don't know. As I said, it's, well, ggplot is quite tricky. And sometimes it takes some time to polish them. Oh yeah, no, that is not an error. It's a warning. It's the same warning that I have. So no, okay. It's a warning.
It's a warning. Okay, no problem.
It's a warning. Basically, the thing that it's telling us is that, yeah, I don't know what summary function you are asking me. I'm going to use min. Yeah. So, and as I said, I wasn't able to do the trace of the problem to run this with no error. So I just keep just with summary because it still gives us the thing that we wanted. Okay.
Yes,
so,
because before
yeah,
no,
go ahead.
Another result on a cluster plot, and no, I don't know why. Then I repaste the command for ggplot, and now I have the correct plot.
Okay. Yeah. I don't know. As I said, it's for me difficult to see. As I said, you have the correct plot at this point. Yeah, it's good. Okay. So let's go to the comings fast. No, I think that is not difficult part. So again, we use the same input, this DG table that we created, so we don't need to create it again. So the first, let's do something simple. We are using the same distance that we used before. So we are going to use with coming of 3. So yeah, let's run coming of 3. Yeah. So we run this. We will have this gene cluster coming free. And then we can explore several things, but the thing that I want to see is how many genes do we have per cluster. So that will be this option. So we run this. This, as you see, this is even worse than the cluster before, because we have 4, 258, and 1. So as you can see, if we need to think in clustering, if we compare these clusters with the clusters that we ran before, that is this one. You see that, oh no, yeah, that was table. Oh yeah, because I modified the cluster. Well, anyway, so yeah, I modified this to do yeah, okay. So anyway, so yeah, we can see that this kind of different, very different from what we got before. Okay. So yeah, so that is one of the problems. So yeah, I personally don't like quite much use comings for gene expression analysis. For other things, it's fine, but not for the gene expression. Okay. So that is with 3, but we want to do it for everything. So we are going to do this loop. So we are going to create an empty list. Then we are going to create a counter. And then we are going to add one to a counter to each of the interaction of the 4. And then we want to print also the results, I mean, of this interaction. But the most important is we want to add something else to this. So if we run this, we want to add a new item to this. So if we run this, okay, so we run the cluster, and then if we say clusters, that clusters, yeah. And then, for example, 1, it will print each of the different k-means that we did, okay? Of course, you have different components, no? So you have clusters, you have centers, thoughts within, for example. Okay, so you still can, so each of these, so for example, size. Okay, so this is giving us the sizes. So, okay, so that is how we change. So you see that originally, when we run the first k-means of 3, we got, let me see, 4, 258, and 1. And now we are getting 1, 258, and 4. So still we have the same number, but it changed the order. So why? You may have some differences when you are rerunning k-means, not depending of, because it's kind of trying to adjust this centroid, and sometimes because keep in mind that the centroids start at random. Okay, remember that the first step is you put the centroids at random. You may end it with different results too. Okay, so that is the reason. Okay, so yeah, we run from K2 to 10, and then the last thing is we want to selecting the optimal number, well, maybe it's not a good word, is just to compare clusters. No, I already have this FCT. So a good example of a line just comparing to cluster will be this one. Sorry, is one. So if we paste this is different parameters, okay? And as I said, I may not have much as much, time to explain which one is the best, because as I said, all these different parameters give you different perspective of which one is the best, okay? And at this point, it's difficult for me to interpret that, no? But for example, if I have math to say which one is the most compact one, I would say that the one that is that has 2 clusters is more compact than the one that has 3. So in some ways, it could be more robust, no? In some ways, you see that the average distance increases a lot when you have three clusters, as the median distance, separation, average, and so on. So, so as I said, it will take much time also to describe which one is, to analyze these different things. But if I don't remember bad, smaller, that is the size of the cluster, more compact that is going to be, more robust could be 2. But as I said, I cannot. You remember that when I present the presentation, you have different options. You also can measure the gaps and so on. But as I said, I will not go there. That is the tool. Okay, questions that you may have about this. I said the last part, as I said, that is I show you the tool, but not evaluating each of the parameters because, as I said, yeah, it can take a long time to explain them. Okay, so let me stop the recording of this again.